Morning everyone. Welcome to the third day of the conference. So today it's like very exciting for us because we have two keynotes lined up from two industry experts. So they have been seeing the industry growing from strength to strength. And the first among this is Dr. Gautam Shroff from TCS Research and Innovation Labs. So he's a vice president and chief scientist in TCS, and he reports directly to the CTO. So before joining TCS, he was a faculty member at the California Institute of Technology at Pasadena. He has also held faculty position at IIT Delhi from 91 to 97. He has been holding visiting positions at NASA, at Argonne National Labs. He was awarded the Young Scientist Award from the Indian Department of Atomic Energy in 1994. So he has authored more than 60 research articles in various areas like parallel computing, software architecture. Presently, I know that he's taking a lot of interest in AI and big data. So he has written two books, one on enterprise cloud computing and the other on the intelligent web. He also has a massive MOOC course that was hosted in 2012, which was titled as Web Intelligence and Big Data, in the capacity of an adjunct professor at IIT Delhi and IIIT Delhi. So one of the prime contributions to our community that Gautam has made, as far as I know, is finding the IKDD. So he was the founding member and chair of the ACMC KDD India chapter. And as I know that it has been growing and growing from that time onwards. So without any further ado, I would like to welcome Dr. Shroff to deliver the talk. Thank you very much.
Okay. It's working? Yeah? Okay. Thank you, Animesh.
Please go ahead.
Good. Thanks for that kind introduction. Oops, you want some help there? Oops, it's a bit.
It's okay.
Okay. The slope is not good. Okay. I have never come to this conference before. I normally go to KDD, AAAI, and such venues, and the India KDD was, as Animesh mentioned, something I set up a few years back. But today I'll talk about IoT. Because I think that was the closest I could come to networking. I'm not really maybe we can raise the volume perhaps, or I'll have to go back to my professorial days and shout a bit, right? So industrial AI and IoT, okay, I think that's too much, right? Okay. So if you think about AI, I think we are in a dangerous situation with AI today. It's at the height of the hype curve, and it's bound to, expectations are high. The title of yesterday's panel itself was, can AI solve all the problems? That seems to be the general flavor of the day. Can AI solve all the problems? It's become a bit of a joke now. So it certainly can't solve all the problems. It's a technology. It's an approach which has been around for 50 years or more, so we have to be a little careful. But let's see what in principle what we have been able to achieve over the past 50 years or so. What we can do in a few seconds as human beings is now within the realms of machine learning and AI. So perception, I mean, with caveats, accuracies and stuff not being obviously perfect, but humans aren't perfect either. Next, what comes next? Looking at sequences. In fact, everything that we do is arguably a sequence. Even vision is a sequence. We're always seeing things in a sequence. So we're now able to do that reasonably well with AI techniques, predicting what comes next. And taking complex decisions, which is traditionally the area of OR, optimization, etc. But it turns out that one can actually do that very, very well using machine learning and reinforcement learning. So that's also something which we're now able to do fairly well, right? So that's prescription, or figuring out what's the best thing to do. And then finally, participating, right? So robotics, autonomous vehicles, drones, are all things which now are able to operate within our physical environment and participate in a realistic way. So these are now become possible. And as a result, a few things have happened, right? I'll come to what has happened in a minute, but there's one big trend over the past 5 or 6 years. For example, when I taught this course, which was Animesh mentioned, this had just started, right? And in fact, it's a big gap of the course, which I never taught it again, is because it's pretty old now. It didn't talk about deep learning, so it's kind of useless, right? It's really becoming, it's sort of eating up everything in a very rapid way. Obviously, just a brief introduction. I mean, CNNs, everybody sort of has heard about them, but this, about a year and a half ago, these things have now become interesting. And we're starting to using capsules and stuff, even for language, right? Which was originally Hinton came up with this for vision. And sequences, of course, these have been around for a long time, since the 90s, early 90s. But now, things like dilated CNNs, attention, transformer architectures, and meta-learning, pre-trained models. I'll talk a little bit about that. These are things becoming very important, especially for sequences. Images, of course, has already been there for a while. And then logic. So deep learning is fine. It's totally unexplainable. How do you sort of marry that with logic? That's something we'll be working on. I'm not talking about that today, but that's a very interesting and a very important area, sort of the neurosymbolic learning area. And then planning and control. So OR, optimization, planning, control, navigation, is all in some sense decision-making exercise. And now deep reinforcement learning are possibly augmenting and even replacing traditional techniques, right? So moving beyond the gaming world, where they have actually achieved significant successes, I'll give you one example how we're actually been able to use this for planning. For there are many other examples which I'm not able to cover today. But what is also done from the industry perspective is there is a huge impact from these new technologies in different sectors. So banking, instead of just taking care of our money, is now able to advise merchants on who they should sell to, because they have a lot of data about who buys what where. Not at the individual level, they're not allowed to use it, but certainly at the aggregated level, right? Insurance wants to prevent rather than provision. So basically, better lifestyles, better driving, et cetera, et cetera. IoT comes in a big deal in that area. Retail, clearly the big battleground with Amazon and the traditional retailers, but blending the online and the physical. Again, IoT and sensors and all that become very important in that area. Manufacturing, smart manufacturing, a lot of people have, I think, talked about it already. But connected everything, I'll talk a bit about that. I mean, what happens when every product is connected all the time to the manufacturer, right? And life sciences, we talked a bit about that yesterday, genomes and connected care. And control systems, Uber, Airbnb, et cetera. These are all now become possible because essentially of this way of doing computing, which is sort of inverting the problem of, rather than writing a program to do something, you just use data to figure out what the program should be doing, right? And what does it mean for people? Of course, it has an impact on people. If you look at the bell curve of expertise or ability, at the sort of the lower end of more, let's call it routine work, claims processing, picking up things in a warehouse, monitoring assets, IT support, robotics, the automation and efficiencies are clearly driving a lot of that work towards automation. And there has societal implications there, but not very critical in my view, but that's a separate discussion. And then at the higher end, things like we've heard the term augmentation, amplification. So really engagement with customers and making knowledge workers much more empowered is what AI has been able to do. And I'll give you some examples of that perhaps, but not in great detail today. So that's the broad big picture, right? So what I'm going to do today in detail is talk about two topics. The first one much more than the second. So the deep sensor analytics for predictive maintenance. There's deep sensor analytics for operational control, which I'm not going to talk about, using reinforcement learning, things like that, but that's a separate topic. And there's as much work on that as I'm going to talk about today. And then I'll do this mainly using videos to show what kinds of things now people are deploying, we are deploying in factories for the factory of the future sort of type of situation. It's just initial stages right now. Okay. Asset monitoring and predictive maintenance. The scenario is that you really get lots and lots of data, right? So you get data from cars, machines, engines, all kinds of stuff. You get data from when they go bad, when they fail, and when they get repaired. You get that offline data as well. You also get data when people are sick. They're also machines of some kind, and we talked about some of that yesterday. And this is all telediagnostic data. And it turns out you can do a lot of things with this data. I'll talk about that in the next 15, 20 minutes, right? So our approach to dealing with this problem is the following. Well, first step is detecting anomalies, right? There are many stages in that. You need to explore. You need to make some quality checks on the data. And a whole bunch of various techniques are used. I'll talk about a few of them. Detecting a problem. There's something wrong. We don't know what's wrong. And then figuring out what's wrong, right? So you want to really figure out what sensors are going wrong, and then from there, what faults might have actually occurred. And then figure out when things might go wrong, right, in the future. Right? So that's the other thing. So if you're able to figure out the remaining useful life, then you're able to figure out all kinds of things about what you should do when, right? So this is broadly the framework that we've been using. We've been doing it on many different types of equipment, gas turbines, pulverizer mills within power plants, and various other things, right? So engines and stuff like that, right? Okay, so the approach, to summarize again, is a little bit more detail, is the real problem with anomalies and faults is that because we're such good engineers, they don't occur that often. So you just can't say, okay, I have good things and bad things, and I just train systems to do it, because especially if you're in Japan, they just don't occur, right? So then you have to figure out what to do. So what you do is you model the normal data. So you have some domain knowledge, what sensors should be used, where, how, and then you have sensor data, and you do a bunch of machine learning, and you have models of normal behavior. Based on that model of normal behavior, you compute some kind of a health index. How close is this machine operating to what is normal? Right. Now, what normal is a very interesting thing. I mean, normal when you're going at 60 kilometers per hour, normal when you're in slow traffic, two different types of normal, right? So the sensor values in your car is very different. So the normal is not so simple, right? Normal also has many different modes of operation, stuff like that. So your model has to capture all of this. And then if your health is low, then you're sort of detecting that this is abnormal. Then you have to figure out why something is low, what's really going wrong. And then when, if you're already not low, when will it be low next? So that's sort of, you can detect, but you can also predict. So that's the most toughest problem, actually, prescribing when is it likely to go bad. Because if you can do it in advance rather than when it happens, then you're able to prepare better for it, right? So this is the overall framework, and I'll talk about each of these one by one. It's all published work, so there's nothing very proprietary about this already now, right? So this was our first foray into this long back in the 2014-15 time. So when a time series is predictable, that means there's something called, there is, in principle, you can predict it, right? So it's sort of some steady state operations, etc., right? Then we can actually train a LSTM network to forecast ahead. And then using, when the trained model fails to predict, then you say it's an abnormal and it's an anomaly. And we use the distribution of the prediction errors to, so you have a likelihood, this is a normal type of error that occurs, or is an abnormal type of error. A normal error is that if you're going at speed X and you press the accelerator and now you're going at speed Y, well, it's unlikely that you'll get a great prediction for the next few seconds because you just pressed the accelerator, right? So That's a normal error. So the error distribution captures that this is normal error. But abnormal errors is that you pressed the accelerator, it didn't go up high enough, or it went down. I mean, that's abnormal. So then that's the kind of abnormalities you detect, not just prediction error, but distribution of prediction error and the likelihood. So you go down and say, okay, there's a forecast, and there's an observed target, and there's an anomaly score, right? This was published in ESNL, and this thing has been cited quite a lot in the past few years, few hundred citations. And we keep getting a lot of queries about this one. But see, the advantage of using this is we've sort of shown that the input layers capture some daily trends, and some things capture weekly trends. So different layers of the network are capturing, as we've been sort of trained, deep networks capture different layers of abstraction, and we've sort of shown this visually also in this paper. And then the other thing is that you can actually model these sort of dependencies, like I just mentioned. So if the accelerator is sort of going high, but the coolant temperature is too low, right? So then there's a problem, right? So in some sense, here it's okay, accelerator is high, coolant temperature is high, but here it didn't happen. It should have happened, it went high, it didn't go. So these dependencies get captured automatically in the deep network, and that's kind of interesting across many sensors, hundreds, sometimes 1,000 sensors, and you capture all these dependencies, right? But now we also have to deal with time series which are not predictable. That there's this fundamentally, things are unsteady. It is just always rising or falling or doing weird things. It's just the way machines work. They're not always in a steady state, right? Especially if you're dealing with drilling, where you have rocks and various impediments. It's not because of your accelerator that things are slowing down, but because you hit something. So it's not a predictable time series. You can't predict when a stone is going to hit, right? But it does hit. So what we do then is we train to reconstruct the time series. So in the past, so for the past so many seconds, you reconstruct it, right? And if it's abnormal, then the trained model is not able to reconstruct. It's an autoencoder type of situation. And you use reconstruction errors to detect abnormalities. And this, we've shown, is able to deal with abnormalities in sort of unpredictable data. So this was ICML workshop in 2016, right? So an example of actually applying this, for example, you've got all these different sensors, and this is normal, this is faulty, this is sort of unsteady region, right? This is sort of normal, this is abnormal, this is speed is sort of going up like this is pretty fine, but this stuff is sort of abnormal. And your anomaly score, which was kind of low, it suddenly goes up right here automatically, right? Now the interesting thing is that, look, this happens, but you also need to figure out why it happened, because you have lots of sensors. I just shown a few, you could have hundreds. Which ones are actually at fault? Because it's just an anomaly score. This is just saying this is something wrong. You don't know what's wrong. So somehow you have to figure out which sensor is responsible for this anomaly, and you do that automatically, because this is, you can't do it with people looking at it. So what we do is we basically have a health index estimator. Is it low? Well, yes. Then you have to somehow find the subset of sensors which are signatures for that fault. So what we do is we use the normal LSTM-based health index estimators, which are either predictive or reconstructive, and then we create a Bayesian network which models the dependency between the health index and all the other sensors. So it's a causal network which sort of captures this. We learn the structure of the network and we model it, and then from there we compute the posterior probabilities of which sensor is more likely to be responsible for this low index. So the index is low, observed. What is the posterior probability of which sensor being responsible for this? And the Bayesian inference just tells you this. So this is kind of interesting way of marrying Bayesian networks with deep learning in a sort of pipelined mechanism. This was covered in ICHCAI in last year in 17. And then, this is an example of this happening. So that the posterior distribution of sensors in the normal situation is, say the temperature sensor is like this. In the anomalous situation, everything is high. So that posterior distribution actually changes. There should be a bunch of low sensor values, but it's not there. The distribution is different. So you just look at the posterior distribution of which sensor changes the most, and you figure out that's the guy which has changed the most. And then on top of that, there's domain knowledge. That look, if these sensors are wrong, it's likely to be this fault. Right? That's where you have to code the domain knowledge that, what sensor is going wrong, and therefore what fault is there. That's where the engineering knowledge is coded into the system. Right? Similarly, for a polarizer mill in a power plant, this is past data, which now is in production, but the plant was actually shut down here, but because of this kind of technique, we were able to detect this 12 hours before that actually happened, and actually show what was the reason for it, right? And this, because of this ability, we were now able to deploy this, because on past data, we could actually show that we could detect. Had we deployed it in the past, counterfactually, we could actually show this, right? Now, this is the tough one, right? How do you figure out when something is going to fail? Because this is easy. So far, I would say not easy, but you detect it and you find out what's wrong, okay? But it's always wrong. You're already in trouble, right? So can you tell me in advance? And that's the tough part. Obviously, you can't tell me in advance if a stone is going to hit, right? So that is out of syllabus. If it's slow degradation, then we can predict something. So your time series, and you have your encoder, decoder, which I just mentioned. You reconstruct the time series. And then you find out, and you have many different modes for this reconstruction, right? So there's this embedding. These middle layers of the network are the embedding space, right? Like word to vec, for example. They're the embedding of behavior. And if you plot them in T-SNE space, which is two-dimensional, you'll see that some are many different modes of normal behavior are there. These things nicely cluster. It's not just one normal behavior. But if your behavior is far away from all the normal modes, then you're likely to be abnormal. And that's a very simple observation, but that sort of seems to work, right? This is robust to noise. There's also figured out how to handle missing values and all that stuff. That's a detail. And this came out in KDD last year, right? But then what about time to life? You can figure out that this is abnormal based on the embedding, but the embedding now, the distance to normal can be computed, whereas in the past, it was just an anomaly score that, yes, my reconstruction error is good or bad. But now, because it's a distance to normal, it's not just a reconstruction error. It's in a distance space, a space with distance. Now you can actually track the degradation of this distance. If you're close to normal, then you're over here. If you go down, you're further and further away from normal. And then that becomes a measure of health. And then how do you do time to life? Well, you look at all your training data, and obviously some of them will have different curves, and you find which cluster of curves you're likely to lie in if you're sort of here, and then you take an average of the remaining useful life of those guys and say, this is what I expect, or to take the one with the lowest variance, right? Which cluster has the lowest variance? So that tells you the remaining useful life. And using this, we today have state-of-the-art results on this NASA turbofan engine data set. And that's nice, clean data. But in real life, this is a problem. It doesn't work as well. So that's a caveat. So this is still an open problem, how to solve this very well. I'll give you a few more examples. So, when you're close to failure, you're very good, actually, at detecting failure. When you're far away, you make a lot of mistakes. Not that many, but you make a whole bunch of mistakes, right? Which is kind of expected, right? But this was in KDD 2017, which I just mentioned, right? Now, the problem with that technique is you actually need a lot of instances to compute those curves, that you actually want to be able to say when something is, otherwise how will you find out the remaining useful life? You have to compare the curve with training data. But like I said, if you're in Japan, nothing fails, right? So where are you going to get these failures, right? But you also have a lot of engines which are just working, and they haven't failed. But that's data. That something has actually run for this long and it has not failed. You have to use that. And so what you need to do is, this is the sensor data. In reliability terminology, it's called sensor data. Data which has not yet failed typically is thrown out of your analysis because it's not failed. But you need to use that. So you really can't train these things, these techniques which I just talked about on reconstruction error type of things end to end with sensor data. But what we can do is something new. This is ordinal regression. The ordinal regression, the first deep ordinal regression paper came out about a year and a half ago from Bengio's lab. And we sort of looked at that and said, look, he was doing it for healthcare data. And said, look, this looks cool. And it was not sequential, so we started doing LSTM on it. And this sort of nicely works. What you do is, this is traditional regression. Suppose you're trying to just predict the remaining useful life, number of days to failure. That's metric regression. And that's the sort of the naive way of doing things. Ordinal regression actually is you're not predicting a number, you're predicting whether it's 1 day away, 2 days away, 3 days away, 4 days away. And obviously if it's 4 days away, it's also at least 3 days away, at least 2 days away, at least 1 day away, right? This is a correlated set of outputs. If this is 1 and the rest are 0, these 2 are 1 and the rest are 0, it can't be 0 and 1. So it's a ordinal output. And now, if you have data which is censored, that means that some data, the engine has not yet failed. So all you know is the remaining use, sort of the time to failure is it has at least run till this much time. So you know that much, right? So you use that it has not failed up to now. So you know that those are 0, right? So you just make those guys 0, and that allows you to use all the censored data as part of training, right? And then that sort of works pretty well. You get partially labeled training instances. You modify the loss function to take care of all this. And then you can overcome this problem of a very small amount of failure data because things don't fail, especially in Japan. So this came out earlier this year, earlier in 2018 in ICML. So clearly, see, if you don't have a lot of failure data, right? So if you have lots of failure data, then metric regression is sort of pretty good, right? But if you have very little failure data, right, then you get a gain from ordinal regression, significant gain, 10, 12 percentage points in terms of accuracy of your predicting the remaining useful life. So this is kind of important, right? Because this is a very tough problem, predicting the remaining useful life. People say predictive maintenance is simple, I'll predict the remaining. It is not simple, okay? And so, but all these techniques are gearing us towards getting there, right? Okay. Now I'll come to the next little interesting piece. I alluded to it yesterday in the panel about pre-trained models, and the healthcare was just one little part of that. Typically, what you do is you have time series, you have a deep learning model, and you want to compute, either do classification, anomaly detection, forecasting, clustering. But if you train your network on many data sets and on many tasks, right? It turns out that multitask, multi-data set trained network, the embedding layers of that are actually good for new data sets which it has never seen before. Not just new data from the same data set, new data sets, totally different types of engines, totally different types of even humans rather, right? Which are, like I talked about yesterday. So this is what we do. We got the encoder, decoder, the old workhorse, train it on a whole bunch of time series data. It turns out that the hidden layer features that you come out once you have this network, you can just compute the features that it's learned, and it sort of automatically clusters a whole bunch of stuff which you never saw before. So these are T-SNP plots of stuff that you didn't see before, and it works when it's been trained on data which was totally, I'll forget about these, which you haven't seen before. So so this is just an example. I'll just point out what I'm trying to say here. That this column is a whole bunch of data sets which the guy has never seen before. This is all public UCI data sets. And this is a deep network which has been trained on those data sets. Right? It obviously does better than traditional sort of DTW type of classifiers. But this guy, which has never seen the data set before, anything from the data set, not even one time series from the data set, just shove the features in, on top put a classifier on top of that, of course, the classifier has to be trained with some training set, but it has never actually seen the time series. It has only seen the features which the deep network computed. That does better than if actually training on the data set itself, which is quite surprising. That was responsible for some of the results that we saw yesterday, and this has similar applications in transfer learning from one use case to another use case. It's all there in the works. That's not published. I'm not talking about those results yet, right? So now I'll turn to robotics. That was enough about predictive maintenance. Remember, predictive maintenance, once you got anomalies and sensors, you have to have domain knowledge to say what is the problem, right? So that doesn't, I only talked about the machine learning part of it. The domain knowledge part of it is another layer that we have which sits on top of all of this as a different layer. So what's new in robotics? Well, telerobotics, you want to be able to manage large numbers of engines. You want to have immersive experiences. You want to have dexterity, which is still not there. You want to be able to deal with network latencies and stuff like that when doing tele operations. Then you want to be able to control multi-robot situations, so you want to have some kind of a cloud robotics model. You want to be able to do different types of multi-robot task allocations and things like that. And you want to be able to work even when network fails, because if you're doing tele operations, action at a distance, if things fail in the network, the robot shouldn't just stop and create a problem, right? And then you want to deal with knowledge and stuff like that, right? And then grasping and manipulation is a tough problem, so you need to be able to deal with that without having to program things directly, right? Yeah, no problem. Okay, so I'll give you a few examples of what we're doing in this area. So object recognition using deep learning, that was kind of responsible for us being able to do fairly well in the Amazon picking challenge, which is a competition Amazon holds every year on picking and storing things in a warehouse. And be able to do fairly well. Palletization is now what we're using that for in commercial operations. We didn't enter this year because we are too busy with actually commercializing the whole thing now. And now even for loading things into a box optimally, this is that reinforcement learning thing. It turns out that one can use reinforcement learning to actually plan it better. So you can almost human level performance in terms of packing things into a box. It's sort of a 3D bin packing problem, but it's not an easy one to do. There is no optimal solution which is tractable. But you can do it using heuristics, or you can do it using deep reinforcement learning on top of heuristics, and you can do better than your heuristics and almost as well as a human. So what this all adds up to is a factory of the future, where you can have predictive analytics, you can have some AR, VR, which I haven't talked about. You have robots working with everybody, with people, and then you have these unmanned trucks and automatic loading and stuff like that. I'll just show you one video of the kind of things that this allows. So this is the palletizer. This is the truck loader at work. So this picks up things and puts things into a box. This is part of the palletizer. The other part I haven't shown. This is where it's just automatically scanning the barcodes and then does the palletization. This is what this is the mobile mobile material handling unit, where you can actually automatically avoid things. These are things that now are easily possible using robotics. And the palletizer was, let me just see, this guy, which is just sort of does the equivalent of the Amazon picking challenge, but in some sense doing it while creating pallets and picking up things from all over the floor and doing that. So this stuff is now sort of getting commercialized. So I'll close with the next few minutes by just talking a bit about AI deployment in general. So when you have closed loop robotics or a control system, it's kind of easy because you know when you're going wrong, right? So errors can feed back. Predictive maintenance is not there yet, because predictive maintenance, you're just saying that do this, but will the guy actually do it? That's up to the human operator to do it. So that's sort of not really closed loop yet. That's more like an assistant, that you're saying that, look, do something, and then somebody did not do it, and then you have to sort of look at the reasons why that happened and sort of either correct. So you need to have some workflow around that. And then there's automation. If you're just doing some perceptual task and automating that You don't want humans in the loop at all. But as you know, AI will make mistakes, and so you need to have spot checks to figure that out. Otherwise, you'll make a lot of mistakes. Has the distribution changed? You need to do something different, retrain, etc. So people often confuse 3 different deployment models for AI. Not everything is closed loop. Assistant requires a different type of human intervention, and a total automation where you don't want humans still requires human spot checks, right? That's just one point that is very important when you're trying to deploy all these approximate learning-based techniques. Last comments, industrial operations, just like we have NOCs and data center operations, security operations, we could potentially have industrial operations centers. Action at a distance, because now you're able to do things at a distance with automation. But autonomy has a different connotation that weapons can be automated, right? And this, I was part of this UN meeting on this, and this year as well. And it turns out that there are all kinds of fellows. Stuart was also there. It turns out this is the big deal now. People are trying to figure out, and except for one big major country, everybody is sort of aligned towards having some controls on this. That one big major country doesn't want anybody to talk about it, which is fine. But then that's happening now, because now you can actually give an order, go down, kill everybody in this village, and come back. And that's called human-controlled acceptable intervention, which is not perhaps the way we wanted to have it. So this is an area. Quick TCS Research, we have 9 research areas, a lot of things, traditional software type of stuff, hardware, but also physical sciences, material sciences, life sciences, security, and all that kind of stuff, and dedicated programs which sort of make a lot of these things into businesses. And finally, we have more than 500 people in research across 7 locations in India. We focus on real-world impact and derive publications after just demonstrating impact rather than the other way around. And we're looking for people who are interested pretty much in doing that. Okay, thank you. These are the people who started TCS Research, JRD and Mr. Kohli. So I always end with their photographs. Thank you.
Thanks a lot.
Thank you.
Yep.
Saurabh Bagchi from Purdue University. You mentioned about ML algorithms making errors and you being able to compensate for them. So do you see that there is ways of maybe retraining, incrementally training your algorithms in real time as you find out your algorithms are making errors? And sort of a related question is, you also mentioned that domain knowledge is very important to infuse into these algorithms. Are there any formal ways, rational ways in which you can put in domain knowledge into the algorithms that you talked about?
Okay, I'll take the first one first. We did have a paper last year in CORDS which talked about online anomaly detection. So what happens in anomaly detection is when the normal changes, then you're always an anomaly, which is a problem, right? So you have to learn to relearn. So essentially use the anomaly score itself to drive the learning rate back. So if the anomaly score is low, there's no learning happening. If it goes up, then it goes up for a while, but then if it persists, then suddenly a learning rate goes up, and you're actually learning to learn a new normal. So that sort of has worked. We haven't seen that many cases where it's needed, though, because normal changes sort of after a major configuration change, right? And normally people know that, and then you do a retraining. So while it's a good research problem, online learning, and it's not a well-solved problem, in practice we haven't found the need to deploy it yet. Right, we'll probably find it. Yeah. On domain knowledge, sure. The way we're looking at it is, like I said, if you detect what's wrong in terms of sensors, how does those sensors being wrong improve the likelihood, or sort of say what is likely to be the real fault, right? That's domain knowledge coming in. They could come in via rules. It could also come in via traditional diagnostic Bayesian type of settings where you know the symptoms and there's a likely cause. So traditional diagnostic systems or rule-based expert systems can be used to build that in. At the lower level, pushing domain knowledge into neural networks, we've done a little bit of work with inductive logic programming a couple of years back. It's still very nascent, like that sort of logic, meta-interpretive learning and stuff. It's still nascent. And there's been earlier work in the 19s, the K-band work, where you try to use rules to construct the structure of the network and learn other things. But I would say it's at the cutting edge right now. Yeah.
Great talk. Just a simple question. You mentioned about this anomaly detection, and where the critical part is which of the sensors is causing the anomaly.
Yeah.
Now, this question is motivated by what I was reading about the Lion Air crash, and even the one before that, where the problem was with the angle of attack sensors, whether how high, what angle the plane was flying at. Now, here it triggered a thought. I don't know whether it makes any sense. When there is an anomaly, how do you know whether the data that you're getting is the anomaly from the sensor itself or something with the underlying process?
Yeah.
Is that the domain knowledge issue there? Or
very important.
You see what I'm saying?
I see. So that's another very important piece. So when I said that we would look at the predicted the sensors being at fault and their values, there are two things you can conclude from that. One is that there's actually a fault, and second, look, this is physically impossible, and therefore the sensors must be at fault. And there, the physics-based understanding in those rules is very important, right? So something just can't happen, right? You cannot have temperatures of 1,000 degrees Celsius. It's just not possible, right? I mean, maybe you can have it inside a boiler, but you can't have it, somewhere else, right? So it's just it's out of bounds, or these two things just can't be like this. So that's also, so the rules take care of two things: sensor detect faults and real faults. And Peacock, our framework, does that, right? Yeah.
So in the interest of time, we'll take one more question. Yeah.
Okay. Yeah.
My name is Srinivasan. I'm a retired government officer, IAS. I had two questions, two parts. One is, of course, this is all gradually getting into the field of science fiction and much beyond. Now, can you train a network to train other networks in future? Can you unleash it?
Okay.
Second is, on the policy direction, there's artificial intelligence, what we know from the media and other reading from other sources. It has a lot of dimensions which would trouble policymakers, because on one hand, artificial intelligence is going to take over a lot of automation, and we talk about elimination of employment, etc. But although they say that there is no danger to that, but if you ultimately see, considering the extent of population and the aspirations of employment down the line, how will you really address the impact what is going to happen?
I got it. Okay. First one. Networks to train other networks is already there. It's not science fiction. Networks which learn what is the best network architecture and dynamically reconfigure the network which is being trained. So basically, learning to learning network structures is already there. I mean, it's part of the AutoML stream of work which people are doing, and so it's not science fiction. It's already there, right? I don't see a great impact in our work there, but if you talk to what DeepMind is doing and stuff, they're doing a lot of this kind of stuff, right? And so it's something interesting going to come out of that. In terms of the jobs question, I keep getting asked this question. I mean, if you asked what would happen to horses in the 19th century, well, they would be out of work. I know, and horse population has gone down because of cars, right? So there will be impact. But every technology change, including computerization itself, was supposed to have a huge impact on jobs. Instead, it created more jobs. It created this industry, the IT industry. So I don't claim to be able to predict what will it create, but history has shown us that automation improves productivity, improves wealth, improves the economy, and jobs get created. There is short-term disruption. But long-term gain. That's the Luddites have been there since the Industrial Revolution, right? So that's my answer to it, right?
So on the behalf of the organizing committee,
okay.
So we have a small token of appreciation. So may I request Rakesh to hand over the Okay. So we have the second talk today by Dr. Jan Holler. So Dr. Holler is a research fellow at the Ericsson Research, and he has been in Ericsson driving its technology and research strategies, especially in the Internet of Things domain. And he has been contributing to various European Union projects like Sensei, IoTi, and